Here we have a next example where we're looking for a alpha carbon. That's the carbon that's attached to your leaving group, the leaving group being iodine. And I see that it is a tertiary alkyl halide. So that means that we're down here in the bottom row of our grid. And we have tertiary butyl oxide as our attacking molecule, tert butoxide. Do you remember how to envision that? You have a big, bulky base. The big, bulky base of tert butoxide, remember the K is just your spectator ion. And what that's showing us is that it will not be able to act as a nucleophile just because it is so darn big, it cannot make it into this electrophilic carbon. Now, it can find beta hydrogens and form elimination reactions, but it will not be able to form substitution. Just it cannot make it into that electrophilic carbon. It's too big, it's too bulky. So here we have a strong base, strong nucleophile, this column, but this row, so the only possible outcome is elimination. All right, so it cannot act as a nucleophile, but it can act as a base. It is a big, bulky base. That means for elimination, we have to find beta hydrogen. And as I take my highlighter and show, here's a beta hydrogen, here's a beta hydrogen. Those are equivalent. And I have a next beta hydrogen, I'll mark in green right there. So looking at the outcome of an elimination reaction, let's take the what I highlighted in pink first. So here's a carbon leading out to a carbon, leading out to a carbon where a double bond would form from the elimination of the beta hydrogen here. And since these are equivalent, that would be just one possible product. This looks like a di-substituted alkene. Remember, these are just hydrogens on the ends. That's why I left them off. So that is no possibility for cis-trans since we have two like groups on the carbon right here, both leading out to hydrogens. So a di-substituted alkene. What about this beta hydrogen? If we were to take that, the competing alkene would have us go out to those two methyl groups and form the double bond right there. And that is a tetra-substituted alkene. There is no possibility for cis-trans there either because if you notice, we have two like groups on there. So I'll just highlight here and here are the same. Those are methyl groups, so no cis-trans stereoisomers to consider. This would be your major product since it is tetra-substituted. This would be your minor product that is only di-substituted. Alrighty. How about another? We'll keep going and going. Here we have an example of a tertiary alkyl halide. Alrighty, so that's this row. And we have ETOH, ethanol. Envision that, what that looks like. It's CH3, CH2OH. The ET represents a 2-carbon chain, and we have an alcohol group. I want you to know that that is a protonated solvent. Do you see how there's a hydrogen on the electronegative oxygen? Polar, proton, polar, protonated solvent. So that means it is a weak base, strong nucleophile. So this column where we have solvolysis, where the nucleophile is going to be directly the solvent. So solvolysis in an Sn1 reaction. Tertiary alkyl halides undergo solvolysis with a protonated nucleophile. And let's just review. It's always good to just keep practicing. Here is your iodine. We know the rate determining step says the leaving group has to leave. So the very first step, the iodine picks up those electrons and you say minus the leaving group. The rate determining step. 1, 2, 3, 4, 5. There is your carbocation intermediate. So the carbocation intermediate, not a transition state, but an intermediate. And that forms, remember, with sp2 hybridization, it is trigonal planar, meaning that it is flat on the tabletop and it can have a top or a bottom attack. Now, this is not going to end up being a chiral center because I have two light groups. There's a methyl group on either side. I do want to consider rearrangements if possible. And right here, I'm noticing that the carbocation is indeed a tertiary carbocation, so I will not need to consider rearrangements. But if so, it's a good time to pause and reflect. If you're going to have any rearrangements, it would be right here. In the next step, the ethanol, ETOH, acts as the nucleophile and seeks the positive center. And so now when we begin drawing, the oxygen has now attached to the carbocation's missing bond, and you have this structure form where this is now a positive formal charge on the oxygen, oxonium ion, the positive +1 charge on the oxygen. And again, we'll emphasize how unstable that is. And so therefore, we need a proton transfer. So the ETOH acts as a base and deprotonates the ether linkage. And so the final product that we'll end up with, we have our 5-carbon chain. There's the methyl group. There's the oxygen linkage. And here is the ethyl group. That's the substitution on this reaction. You've created an ether linkage. 1, 2, 3, 4, 5. And remember what that really is 2 more carbons there, right? That's what ET stands for. If this were a chiral center, it's not. But if it were, we would consider stereochemistry of having an R and an S configuration, because we would have a front and backdoor attack in that trigonal planar molecule. All right, let's keep trying. Oh, we have a cyclobromate. All right, so here we have at carbon 1 our alkyl halide, and at carbon 2 you have a methyl group in a 6-membered ring. We have a strong base, strong nucleophile in hydroxide. So I'm at a strong base, strong nucleophile, and I have a secondary alkyl halide. So we'll see an E2 mechanism giving us the major products, but there is still a bimolecular substitution reaction as well. So we're going to have a mixture of both. So let's take a look at the elimination product first, since it's going to be in majority, elimination. I remember learning that we have to have an anti-periplanar configuration on the beta hydrogen. For elimination to occur, it has to have the correct stereochemistry, anti-periplanar, which means in this beta position right here, and we have a beta position here. Those are our 2 possibilities for eliminating hydrogens. Well, the yellow will have a hydrogen that is a wedge, and it will have a hydrogen that's a dash. The hydrogen with the dash is anti-periplanar. Perfect. So let's consider that one first. Now remember the mechanism. Hydroxide reaches out for this proton, that bond collapses, and the leaving group leaves. So we form a double bond between the alpha and beta carbon, and don't forget you still have your methyl group down there at carbon 2. And what else could happen? Well, in this group at carbon 2, the hydrogen is the wedge. Is it possible to eliminate that hydrogen? And you're right, the answer is no. Because I cannot twist the bond. It's a cyclic structure, so twisting that bond is off the table, and it's not in the correct position. 2 wedges is actually a Sn configuration, and we needed it to be anti. So the elimination product from carbon 2, this hydrogen cannot occur because it is not in the right position. So we only really had one elimination product, and it would be a di-substituted alkene. What about the substitution reaction? So with substitution, we act as a nucleophile and we seek the electrophilic carbon. So the oxygen reaches out for the electrophilic carbon and forces the leaving group to leave. Now, when this happens, the substitution reaction, since Sn2 100% inverts the configuration, and the methyl group is also still on the dash. So 100% inversion with that backdoor attack. So we would say this is the major product, just looking at our grid, that the elimination reaction is favored, but we would also have the substitution reaction possible where the OH has been substituted in for the bromine and the dash turned to a wedge. I also put this one on the same page just to remind ourselves, if we had a secondary alkyl halide, and this right here is the wedge, just like above, but the methyl group is now on the wedge, that means the hydrogen here is available. So yes, we can have elimination in that particular spot, as well as from the dash that's above it. So here you would actually form two different alkenes. If the beta hydrogen is eliminated here, you would form the double bond here and still have the methyl group as your wedge. Plus, if we took this beta hydrogen, the double bond would form here and still your methyl group as the wedge. Notice this is a tri-substituted alkene and this is a di-substituted alkene. So now this is your major product. And you would still have nucleophilic substitution occur. And this time the leaving group leaves and is subbed out for the hydroxyl group. Notice 100% inversion, and you still have the methyl group coming out down below. And so here you'd have three products where we had two possible hydrogens for elimination instead of just one, like the example above. Notice that the major product would be the tri-substituted alkene. So there's a variety of other substrates we should consider as well, instead of just alkyl halides. Now, the entire topic has been alkyl halides, where the halogen acts as the leaving group. But what about other leaving groups? In this section, we're going to entertain some sulfurs and some oxygens. There's a variety of alternatives to alkyl halides for substitution and elimination. And one common one is an alkyl sulfonate, Mesylates, tosylates, triflates are excellent leaving groups, and that's exactly what we want to have happen. We want the leaving groups to leave. They're quite large, and so we usually use abbreviations. OMS, hear the sulfur in there. OTS, hear the sulfur in there. And then of course, this right here is triflates. So an alkyl halide, the leaving group is the halogens. An alkyl sulfonate, the leaving group is a sulfonate. Here you have an alkyl mesylate. Then notice we have a methyl group here instead of an alkyl group here. And an alkyl tosylate, we're seeing an aromatic ring in there. And an alkyl triflate, you have fluorines in there. So those are just some interesting leaving groups, although the mechanism is exactly the same. So if I look at an example here, when you see OTS, I want you to just think of that as a very, very good leaving group. OTS is the tosylate. It's a very common one used in our book. The tosylate, OTS. And do you see where that's looking right here? I just want to make sure you see it. This guy right here. Instead of drawing that out, a tosylate group, we just simply abbreviate it to say OTS. When you see that, know it's a great leaving group. And that's exactly what happens, isn't it? It leaves. And so here we have a secondary substrate. That's this line right here, secondary substrate. OET negative is a strong base, strong nucleophile. So we will see both elimination and substitution in a bimolecular format, bimolecular collision. So let's consider the elimination first. The elimination will have two beta carbons that are equivalent. There's no kind of substitution on that six-membered ring, so those two green carbons are indeed equivalent. So I'm saying if I took the hydrogen here, I would form a cycloalkene. And again, if I took this hydrogen here, I would form a cycloalkene, and these are exactly the same compound. So we do not have more than one elimination product. They're the same. So a cycloalkene forms with elimination. What about substitution? With the substitution, remember that the O goes to the electrophilic carbon and the leaving group leaves. And so we substitute. The OTS turns to OET. Now think about what that really looks like. You have an oxygen, carbon, carbon. This is an ether linkage. You turned this tosylate compound functional group into an ether functional group. Now what would be the major product? Well, the major product we see is the elimination reaction. We can see that in this grid. And the minor product would be the substitution with an ether linkage. OTS with sodium hydroxide. OTS, I want you to know that that's just a very good leaving group. Tosylate. Say that in your mind. Tosylate. OTS is a leaving group. It has a sulfur compound and oxygen attached. This is a secondary substrate. This is a strong base, strong nucleophile. So again, we're in the same prediction here of beta elimination and a bimolecular substitution. Let's consider the elimination first. The elimination has two positions of beta hydrogens, and so we'll have to consider both. Let's consider carbon 1 to carbon 2 first. In this beta elimination, I would create the double bond between carbon 1 and carbon 2. 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 carbons in that chain. Remember how we did this. Just to remember mechanism, the oxide reaches out for the beta hydrogen, that bond collapses and the leaving group leaves. So that's how we ended up with one hexene. I do not have to consider cis-trans because on that first carbon we have two like groups. Those are both hydrogens, so there is no possibility of cis-trans conformations. All right, let's consider the beta hydrogen here at carbon 3. So again, if I reach out for, let's say the oxide goes for this beta hydrogen, that bond collapses, you now have a double bond, 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6. You'll have a double bond between carbon 2 and carbon 3. This would be known as 2-hexene. However, I do have to consider cis-trans conformation. So here I'm noticing that the two carbons in the double bond, the priority here is down below the plane, the priority here is above the plane. So this could either be considered an E or a trans. Either nomenclature is fine. Trans 2-hexene, or you could say E2-hexene. They are both perfectly acceptable. But that's telling you that the priorities are one above and one below the pi bond. So there is a stereoisomer to this. So I should say and, not or. So I have 1-hexene, trans 2-hexene, and you would have 1, 2, 3, 4, 5, 6. There's your cis conformation of 2-hexene. 1, 2, 3, 4, 5, 6 carbons where the double bond in is a cis conformation. Of course, you would know that this is the major product, the trans configuration. This is a minor product because it's only di-substituted, and this is also a minor product because of the cis conformation being less stable than the trans conformation. So we had 3 possible products just from elimination. We still have to consider the Sn2 substitution. So let's redraw 1, 2, 3, 4, 5, 6. At carbon number 2, we have a wedge, and it's OTS. The electrophilic carbon is right here. Here is our nucleophile. Notice my nomenclature has changed. You're now acting as a nucleophile, whereas in elimination, it acted as a base. The nucleophile seeks the electrophilic carbon, and the leaving group leaves. We called this a backdoor attack. And so we have to remember the stereochemistry is always 100% inversion when I look at this mechanism. 1, 2, 3, 4, 5, 6. And now we've placed on a hydroxyl group, and it has the opposite stereochemistry, the opposite configuration, the dash instead of the wedge. And again, I would consider this a minor product. Sn2 reactions in a secondary substrate are the minor product to the elimination. But we had 4 products, 3 of them from elimination, 1 of them from substitution. I'm going to keep practicing. Here I see a SH negative as my nucleophile, and my leaving group is the tosylate compound. SH negative, strong base, strong nucleophile. The leaving group is on a secondary alkyl halide. So let's do elimination first. With elimination, I have 2 possible beta positions, but both of them will be equivalent. So with the leaving group leaving, I'll form a double bond. It will be cyclohexene. How about for substitution? Well, substitution would say now it's going to act as a nucleophile and the leaving group leaves. So the sulfur, just like oxygen, it has rich electrons, is going to seek the electrophilic center, forcing the leaving group to leave. And so when it substitutes out, you simply place on an SH functional group. The thiol is not a chiral center, so I don't have to consider inversion. So here we have just 2 products, 1 from elimination and 1 from the substitution. We know that the major product would be from elimination and the minor product would be from substitution. We landed right here in our grid. Keep going. Sodium hydride, NaH. That means H negative is your attacking molecule. Notice that that falls in this category. It's a strong base, weak nucleophile. Remember, a nucleophile seeks the positive carbon right here, and we said hydrides can never ever be a nucleophile. And so with that, we know that it's going to act as a base only. So we have a secondary alkyl, I'll say a secondary functional group there for your substrate, but elimination is your only choice. And elimination means I have to consider the stereochemistry where it's anti-periplanar. So that means in this spot, the hydrogen is in a wedge that's not correct. That's a Sn orientation, and so this is a nope, it's not going to work. But over here, I would have a hydrogen in the correct position, so that will be my only spot of elimination. The hydride reaches out for the anti-periplanar hydrogen, so you just form a molecular hydrogen. That bond collapses and the leaving group is leaving. So you have by the time we're done. The methyl group's still down here on a dash, and the double bond formed right here. And there is no possibility of stereoisomers there, so that is our only product. How are we doing? Have we done enough repetition? One more functional group I'd like to talk about, and that's an alcohol. And this is very, very common, especially when we get to chapter 11 and you start planning synthesis. Alcohols can be used in substitution and elimination reactions, but the starting material, the hydroxyl group itself, is a terrible leaving group. So since this is a bad leaving group, we have to convert it into an alkyl halide to make it a good leaving group. So the strategy is, if you have an alcohol, ROH is an alcohol, and you'd like to convert it into an alkyl halide, we can do so by using a reagent of hydrogen bromide or hydrogen chloride, hydrogen iodide, but it allows you to take the hydroxyl group and convert it back into an alkyl halide. And let's take a look at this. This is because water is a good leaving group. We want to make sure we can convert it. So here we have an alcohol. Sitting on the arrow is the acid, it's the strong acid, HBr. The alcohol can reach out to deprotonate the acid and the bond collapses. So notice now bromide is now a perfectly good nucleophile. You generate a nucleophile by protonating the alcohol. The alcohol is a terrible leaving group, but by protonating the alcohol, you have a very, very, very good leaving group in a water molecule, right? That now protonated alcohol, same as saying a water, H2O, is a very good leaving group. Now the nucleophile that was generated a moment ago acts as, seeks out that electrophilic carbon, forcing the leaving group to leave. That's a bimolecular collision. You've exchanged onto that original compound an alkyl halide, and the leaving group left. There's your water molecule. So when I'm doing a synthesis plan and I have a hydroxyl group, I notice that I can change that poor leaving group into a good leaving group by protonating the alcohol. And by using HBr or HCl, I not only can protonate the alcohol, but I can generate the nucleophile that can then proceed on with the Sn2 mechanism. So for example, if I have a mechanism that's either Sn1 or Sn2, primary alcohols react via Sn2. Tertiary or secondary and tertiary are going to be Sn1, and that's really just the mechanism to achieve the same outcome. Here you have a tertiary alkyl halide. Notice that we reach out and protonate the alcohol. So this is a protonated alcohol. This is a poor leaving group. This is a great leaving group. And to do so, we just used HBr. Two things accomplished. We protonated the alcohol, made it a better leaving group, and that's what the leaving group does. The leaving group leaves. Here is our carbocation intermediate. Now the bromide can attack either direction, right? This could be a back door or front door, because it's a trigonal planar, so both will occur, and so you'll have that tertiary alkyl halide form from a tertiary alcohol. Tertiary alcohols, secondary alcohols use an Sn1, and when we look at primary alcohols, we'll see that as an Sn2 reaction. I also wanted to consider the elimination process of an alcohol, not just substitution, but also elimination. When you see sitting on the arrow very, very concentrated, strong acid, especially with elevated heat, Those are your clues that this is an elimination reaction. Now, an elimination says here is the alpha carbon, this is the beta carbon. You are going to eliminate a beta and the hydroxyl, and that's where the water comes from, minus HOH. These are commonly called dehydration, eliminating a water molecule. We started with a primary alcohol, and we turned it into an alkene through a dehydration elimination process. Now remember the mechanism. If you think about the acid, think about the hydronium ion. The H3O plus is the acid ion. And so H3O plus, we protonate the alcohol, right? That bond collapses and you've made a water molecule. Now that's going to serve as your base for the elimination. But right now, we've protonated the alcohol. We've turned this very, very poor leaving group into a very, very good leaving group by protonating the alcohol. Now that we have this, we're ready for the elimination. The base will eliminate a beta hydrogen. That bond collapses, the leaving group leaves. All of that occurs in a concerted mechanism, and you form an ene along with a dehydration product of water. So we can have substitutions with alcohols, we can have eliminations with alcohols, and we're looking really for converting the alcohol first into a protonated alcohol. So here we have, looking at this, 1, 2, 3, a tertiary alcohol. That carbon attached to the hydroxyl group, looking at hydroxyl group as a tertiary alcohol. So we predict an Sn1 E1 mechanism with tertiary alkyl halides. So the first step, notice that this oxygen is going to reach out for the hydrogen. Just think of that as HBr, where that bond collapses. And the first thing we've done is to protonate the alcohol. And that would now have a positive formal charge, a protonated alcohol. Now remember, this is the mechanism would be Sn1. So the next step, the leaving group has to leave, the unimolecular leaving group. And so at this point, you would have a carbocation intermediate. Then you would see that bromide that you generated a moment ago acting as a nucleophile or a base. We'll do the substitution first. If the bromide acts as the nucleophile, we would then have a substitution reaction where the bromide has switched places with the alcohol. Now this is not a chiral center, so I don't have to worry about inversion. This would be a racemic mixture of R and S if it were a chiral carbon, but it's not. So I'll just draw that in as bromide. If the carbocation now comes this direction and we do, here we did Sn1, let's think about E1, elimination. The bromide then is going to go for a beta hydrogen. And I can actually see two positions of beta. Here's one, and I have two equivalent places here. So two different elimination products will form. So as the bromide reaches out for a beta hydrogen, just kind of think about what's happening, that bond collapses. And so one possible product in elimination, here's still your methyl group. The double bond can be here. And in a minor product, there was a beta hydrogen on top of the methyl group, so you could form that as well. This would be di-substituted. This would be tri-substituted, so that would be your major product in elimination. We had a substitution. We had two products from elimination. Same thing here. Predict the major product for each. So now all of a sudden I'm seeing concentrated H2SO4. I just want to emphasize, when you see HBr, you're really just thinking along the lines of substitution, but we have competing reactions always with Sn1, E1, and so you'd have those occurring. But when I see the concentrated sulfuric acid and heat, I want you to really focus on elimination through the E1 mechanism as well. And I'm just going to bring back that previous slide. When you see HBr on the slide, notice that you've converted into a tertiary alkyl halide. Tertiary alcohols convert to tertiary alkyl halides. In eliminations, you're going to favor that product by concentrated acid over heat. So when I see HBr sitting on the arrow, I want you to think substitution. And when you see concentrated sulfuric acid, I want you to think favoring the elimination reaction. So the major product is substitution between the alkenes. The tri-substituted would dominate over the di-substituted, but these are less prevalent than the substitution product. Down in this direction, we're favoring the alkene, the elimination, and I can see, whoops, I turned that into a pentane. At this point, I would have two possible products here and here. And this, of course, would be the major product for elimination as well. So when I see HBr, think substitution as your major pathway. When you see concentrated acid and elevated heat, think elimination as your major pathway. Draw a plausible mechanism for the following transformation. So I'm going to recognize this is a tertiary alcohol. So my mechanism has to be Sn1. That an Sn2 would be too crowded for an electrophilic. Now think about, this is substitution. It's not elimination. I did not see a double bond. I only see a substituted group. So Sn1 is my mechanism. So we would know that HBr in our first step, and I'll just maybe draw it this way. Here's HBr. The alcohol reaches out for this proton, this bond collapses, and we've now 1, 2, 3, 4, 5, 1, 2, 3, whoops. 1, 2, 3, 4, 5. Looks like a W. Here's this, and now we've got a protonated alcohol. And let's remember to always be sure to put that positive charge on the oxygen. It's oxonium, a +1 formal charge. And now remember, we've got a leaving group, or this bromide will act as the nucleophile. So now in the next step, the leaving group has to leave. The leaving group leaves to form a carbon cation. 1, 2, 3, 4, 5. Here's your methyl group. This is a carbocation intermediate. From there, the bromide, who is now electron rich, is going to seek the electrophilic carbon, which is the positive charge. 1, 2, 3, 4, 5. And right here is the bromide attached. This is not a chiral carbon. It has a plain, two like attachments. And so therefore I don't have to consider a racemic mixture in my product. There's a plausible mechanism using a unimolecular rate determining step. We protonated the alcohol to turn a poor leaving group into a great leaving group. Then the leaving group leaves and the substitution proceeds. When I see concentrated acid, H2SO4, I want you to think about that as the hydronium ion. Hydronium ion there is the acid ion. So again, thinking elimination with elevated heat and strong acid, the first step, we're going to protonate this poor leaving group and turn it into a good leaving group, and it does so by protonating the alcohol. and that now contains a positive formal charge. That's the oxonium ion. So step 1, you protonate the alcohol. That's the same first step, substitution or elimination. Now the same next step, the leaving group has to leave. And in doing so, 1, 2, 3, 4, 1, 2, 3, 4. Here is the positive carbonium ion. This is the carbocation intermediate. It will not have a chiral center. I see 2 like groups. But now in the next step, since we're promoting elimination, the water molecule, remember here, the water molecule left, that becomes your base for the beta elimination. That means the hydrogen has 2 spots to look for. Here's a beta hydrogen in this position, and I have 2 like beta hydrogens here on those carbons. So we'll end up with 2 possible conformations. Now remember, the mechanism says this oxygen is going to seek a proton. Let's take this proton first. The bond collapses and we form an alkene. 1, 2, 3, 4, and then the double bond going here, leaving a methyl group here. This is a carbon attached to 2 hydrogens, so there's no cis trans possible. And so you have 1, 2, 3, 4, 5. This would be 2-methyl, 1-pentene. What about taking this beta hydrogen? And there we would say, if that hydrogen was abstracted, so again, the base reaches out for this proton, the bond collapses. You have 1, 2, 3, 4, and then remember this 5 is coming here, and the double bond now forms here. 1, 2, 3, 4, 5 carbons in your longest chain, and you have a methyl group off of that second carbon. So 1, 2, 3, 4, 5 carbons in the longest chain. So here we would have 2-methyl, 2-pentene. Do we have stereoisomers to consider? Nope, because these are 2 like groups, and so therefore there is no cis and trans. So the major product is the tri-substituted alkene. A minor product would be the di-substituted alkene, and just as we had predicted, the major product came out to be the elimination product there of 2-methyl 2-pentene. And wrapping up really with your last section, just to consider kind of the entire chapter. In it, I can't tell you, I understand, it is a big chapter, and it is so fundamentally important from every chapter forward. This is your foundation for mechanisms. We keep adding more and more and more reagents to our toolbox, but if we have a fundamental understanding of predicting outcomes, you're going to have a very easy journey through organic chemistry. If you start trying to memorize outcomes instead of understanding why the pathways occur, you're going to have a very difficult time in organic chemistry. And remember, the whole point to organic synthesis is to make valuable, complex compounds from cheap and readily available starting materials. You now know how to make a variety of compounds starting with an alkyl halide. I would suggest flashcards until you can commit to memory these particular pathways. Starting with a primary alkyl halide where R just represents a carbon chain. We can change in a substitution. A substitution means exchanging one functional group into another. Using a nucleophile such as cyanide, Cn negative, we can exchange a bromide into a nitrile group. Here, notice that our nucleophile, right here, sodium acetate, the acetate can act as a nucleophile, and I can exchange a bromide and create an ester. You can see how this is a carbonyl carbon, and you've created an ester functional group. So the selection of your nucleophile is critical. I mean, what kind of molecule do you want to make? Do you want to make a ester? Pick a nucleophile that has the correct structure for you. You want to make a nitrile? That becomes your nucleophile. You want to make a thiol? Select a nucleophile that puts SH on the end. You want to make an ether? Start with an ethoxide. OCH3 negative. We'll add on and exchange places. Those are all substitution reactions. If you want to promote elimination, you might want to consider using a big bulky base or a hydride where only elimination can be produced, and you'll form an alkene. If I'm given a tosylate compound, the tosylate is an excellent leaving group. The leaving group leaves, and I created an alkene. Notice this is also a tosylate compound. I can convert an alcohol into a tosylate compound and turn a poor leaving group into an excellent leaving group. I can take HBr and get back an alkyl halide. We went through that particular structure just a few slides ago. We protonate the alcohol, the leaving group leaves, and the bromide then attacks the nucleophilic center. If I start with an alkyl halide and add hydroxide, that's a strong base. A substitution occurs, and I've converted it into an alcohol. I suggest really getting familiar with elimination and substitution so that you are comfortable in predicting the outcomes. Select the correct alkyl halide, selecting the correct nucleophile to make the substance you're after. And remember, there's a different order in terms of tertiary alkyl halides. Spend some time with tertiary alkyl halide synthesis pathway. If you use a big, bulky base, I only expect elimination, and it will favor the Hoffman product, the least substituted alkene. If I start with an alkyl halide, tertiary alkyl halide, and I put a strong nucleophile, strong base, NaOH, I can favor the Zaitsev product, the most substituted alkene. Concentrated acid produces the alkene. Adding water has a substitution into an alcohol. Adding HBr converts the alcohol back into an alkyl halide. Here's your tosylate compounds. Converting an alcohol into a tosylate has a poor leaving group convert into a very good leaving group. The leaving groups leave, and I can make an alkene through elimination. Flashcards. Spend time to where you're comfortable in predicting outcomes. This will make Chapter 11 go so much easier. Chapter 11, it's just simply called synthesis. Your job will be to create pathways to form molecules that you're told to create from starting materials. So when thinking about how to make something, we start about looking at the product first. If we were building a brick house, would you imagine what the house looks like first and then decide where the bricks would go? Organic synthesis is the same way. The approach is called retrosynthetic analysis, and you're going to practice this over and over and over, just thinking backwards. What does the molecule look like that you want to make? And then, what are the pieces you need? That's supposed to be an arrow. What are the pieces you need to get there? This is a retrosynthetic arrow. It's saying the product leads, or it's coming out of what major building blocks. And as you practice and practice the retrosynthetic analysis, you'll become so much more proficient at creating synthetic pathways. And that's truly the ultimate goal of an organic chemist, is to synthesize molecules. Suppose we wanted to create the following ether. Here's a 2-carbon linkage on one side, 1, 2, 3, 4 carbons on the other. 1, 2, 3, 4, 5 carbons on the other. 2 carbons over here. So this would be ethyl, pentyl, ether. You want to make that. Well, what are you going to do? First, identify a bond in the target molecule that can be made using a reaction you know. In other words, where can I kind of separate that molecule into 2 separate pieces? And as you think about breaking this ether into 2 parts, one part will become the substrate and the other part becomes the nucleophile. Because this is not elimination, it will be substitution. I don't see any double bond. So that's my clue that it's going to be substitution and not elimination. Alrighty. So really what you're deciding is, what are my 2 pieces? If I need to make an ether, I need a substrate that's an alkyl halide, 1, 2, 3, 4, 5 carbons long. That's the left side of your ether. And I need a nucleophile that's 2 carbons long and would contain the ether linkage. There's your nucleophile in sodium ethoxide. We can make this by between an Sn2 reaction. We would have an alkyl halide. We would have a nucleophile in the alkoxide ion, and we're just thinking backwards. So this would be a very plausible synthetic pathway where the substitution will occur on a primary alkyl halide with a very strong base that favors substitution. You know, there are 2 carbon to oxygen bonds in the ether, so we could have envisioned an alternate pathway. Again, if we have an ethyl side and a pentyl side, I could have easily chopped the block here, and instead of a 2 carbon oxide, we could have a 5 carbon oxide and a 2 carbon alkyl halide. So often when you think backwards, there's more than one correct way to get to a product. One is not any better than the other. We could have chopped our molecule here, made this the alkyl halide, and this turns into the nucleophile. Either direction would get you the same product. Now, in the last kind of reflection part, verify the reaction you've proposed is reasonable. Draw the reaction in the forward direction and make sure that you would contain, get out that desired product. So just reflection on, does it make sense? And you'll have an opportunity to kind of think through of those in terms of, does this pathway make sense? One of the considerations, for example, here is an ester you're told to make. An ester has a carbonyl carbon next door to an oxygen. Would it make sense, and as I consider what kind of nucleophile, what kind of alkyl halide, what if I were to cut the bond here and we would have a carbon to carbon and my alkyl halide would be here, and that would make my nucleophile the alkyl halide plus the nucleophile. Well, this makes sense. This is just ETO negative, and I'd put on a positive ion to make sure it was electrically neutral. This is a valid nucleophile, but is this a valid alkyl halide? And the answer is no, because this is an sp2 hybridized carbon. And we learned, maybe even on the very first section, that nucleophilic substitution reactions, Sn1, Sn2, E1, E2, all of this must occur at an sp3 hybridized carbon. So that is not a valid structure, meaning that I only have one possible correct answer, and that's to cut the bond here. So we need to make our nucleophile contain that double bond oxygen. There's your nucleophile, and then your 2 carbon alkyl halide could serve as your substrate. That would be a valid starting material to create your ester compound. Here's your job. Make this. And so just think about the easiest way to make this compound is to break this bond and make your nucleophile, the acetonitrile Cn negative. That's your nucleophile. And then your alkyl halide, 1, 2, 3, 4. Your alkyl halide would be a primary alkyl halide. That would work perfectly. So here we've just made an alkyl halide, which is your substrate, plus your nucleophile, which would be Cn negative. And you might as well make sure that you put a spectator there as well so that you have an opportunity to create an electrically neutral compound. Every negative ion must have a first name. And when you make that, you can see a bimolecular substitution occur where the carbon reaches out for the electrophilic center, the leaving group leaves, and you have a substitution reaction to create the nitrile. And that's exactly what you did. You broke the bonds, you had an alkyl halide, and you have the nucleophile. That's as easy as that one gets. And the last thought I'll leave you with wrapping up your chapter, which is the better retrosynthesis for the given target molecule, and explain your choice. All right, this is what you want to make. Make this. Notice here the double bond, 1, 2, 3, 4. So you would have 4-methyl cyclohexane. We do not need to put a 1 because you know that the priority is to the double bond. So 1 cyclohexene is not needed. You know carbon 1 to 2 is the double bond. You want to make 4-methyl cyclohexene, which is your better starting material. Well, this definitely I want you to think about is elimination, because I can see a double bond. I don't see substitution at all. I see a double bond forming, so that means elimination. So we have to consider the beta positions, and the beta position is here and here, and in this molecule here and here. So if I want to form 4-methyl cyclohexene, I would actually have 2 possible products here. I could form a double bond here, and there's that methyl group. I could form the double bond here, and those are different from each other. 2 different possible answers. Over here, these 2 are equivalent positions, and therefore in the elimination process, when I form this one product, that's supposed to be a methyl. Oh, Linda, that's not very neat. There. The elimination product is exactly the same if I take it from here or here. And so since this is only one possible product, that's your better choice. So you don't have competing major and minor products. If you want to have only the target molecule form, pick the best substrate to not have more than one option of product form. Oh my gosh, you've done such great work. We've made it to the end of chapter 7. You have survived. It's a lot to process. It's a lot to digest. And I just want to encourage you that this is such a fundamentally important chapter. You cannot overstudy. All right, I'm here to support you. Good luck.